यस विपुल जी, आप सुन पा रहे हैं?
Hello.
Yes, yes,
Yes,
sir.
sir. Yes, sir. Now it's audible, na? Okay.
Yes, it is audible. Please start.
Hello.
Yes, sir. We can hear you.
Okay. Okay, sir. Thank you, sir.
Fine.
So,
You can share the screen.
I am sharing my screen.
Yes, you are co-host, so you can do it.
So, is it visible? My screen is visible or not? Hello.
Yes, it is visible, sir.
Okay. Okay. So, good evening, everyone. I am Vipul Panchal, and we will discuss today intelligent control of renewable energy system. Okay. So these are the some points which we will going to discuss, like what would be the architecture, and what would be the controlling architecture software, then the parameters, important parameters like MPPT and the inverter control and the closed loop control of current. Okay. And the block diagram and circuit diagram of the system. So in this presentation, we will discuss the software as well as hardware also. Okay. So all things we will cover. Okay. So in renewable energy sources, we will discuss the wind turbine emulator and solar array simulator, fuel cell, supercapacitor, battery bank, and load bank. That could be L load, C load, or R load. Okay, and in wind turbine emulator, we will discuss the converters, inverter, and the controller also. Which type of controller we have used in renewable energy sources. Okay, so in architecture plan, first we did the simulation, and after that we did the hardware in simulation, hardware in loop simulation using the NI controller. That controller is stereo based controller, and we separately tested the solar array simulator and wind emulator, and after that we did data logging of battery bank and others like supercapacitor bank, fuel cell, RLC load. So we tested separately each component of the renewable energy sources. Okay, so like that way we made our setup. And control architecture, we will discuss the converter lead to a particular controller. Like if PV converter, or it is like a super capacitor converter, or and we will discuss that control algorithm of that converter. So converter control and the MPPT algorithm, which type of MPPT algorithm we have used and we can use to make it smart, and the DC link control. So that DC link, I will show you the block diagram, so you will get the clear visualization. So okay, and after that, how inverter we are going to synchronize with the grid, and energy management, that program. Okay, so this type of control or architecture we will discuss, and the key parameters like what is the center of attraction in this system, like MPPT of PV and wind. So various type of MPPT techniques, and battery profile. We are taking the logging the BMS data. Fuel cell, how we are going to control the fuel cell. There is a 3 types of wind profile, like manual mode and table mode and the simulated mode, and a PV like that wise PV profile also. Okay, manual, simulated and table mode, we can give the data according to our requirement. And the load, that load RLC load, we can control that load in the constant power control and the constant current control in both mode. Okay, and we can create the grid disturbance using the grid simulator. Okay, so this is the complete like and okay, now in this like component wise, what how we will go through the component wise. So first we will see the how it is physically visible, the physical appearance of the component or any like product, and then we will have the block diagram, the circuit diagram, protection component, and controlling aspects of that particular component, and at the last we will have the screenshot of the levy program. So hello, uh, hello, am I audible to everyone?
Yes, sir.
Oh, okay, okay. So this, you can see, this is the complete renewable energy based system, 30 kilowatt system. So it have the like you can clearly see in the middle of this that picture, motor and the generator. So that DC motor, that light blue color is the DC motor and the dark blue color is the PMHG, and in the between we have the gearbox. In the left hand side we have that acrylic box, aluminum profile based acrylic box, that is super capacitor bank, and on the top of the table we have the solar array simulator, and under of table that black color box, that is battery bank, and the right side of that motor test bench we have that control panel. Okay, and most right side we have the grid simulator, and between control panel and the grid simulator we have the RLC load bank. And here you can see in the picture that fuel cell. So I will show you the pictures of every component in the further slides. Okay, so that are the components we will discuss, and how we will make this like a intelligent. Okay, so we will discuss it later. So this is the block diagram. So in that PV, wind, fuel cell, and the battery, supercapacitor, all are connected to a common DC link, and that common DC link connected to the grid through a inverter. Okay, so how we will achieve, like we have like all the components. So first we will do the predictive, we will have the predictive layer. That layer will predict about the solar and wind, like wind data and the solar data. Okay, so that AI based algorithm which will predict the irradiance of the irradiation of the solar. So according to that we will program will generate the power, and that prediction layer also predict the wind speed for particular days. So it have the data of 1 year or 2 year. So according to that it will predict the output like sun irradiation of the sun and the wind velocity. So first layer we have prediction layer. Second layer is like real time control layer. that real-time controller is CRU. So that controller will control the all individual component, like wind emulator. We are controlling using the main controller, wind emulator, solar array simulator, battery bank, fuel cell, inverter. We are all component are controlled using the main controller. So that is real-time controller based on the CRU. After that, we have the energy management layer. That layer will uh, control the load, like sorry, it will manage the load on the basis of priority. So we can set the priority of solar, like first, if load is demanded the energy, so who will give the energy first? So we can make it priority based, like solar can give, or wind can give, or battery can give, or fuel cell can give. So first priority is set for solar is set on first priority. After that, based on the wind availability, second priority is wind, and third is battery, and fourth last one is the fuel cell. So like that, the third layer is management layer. So it will manage the load energy. Okay. And fourth is communication and data, like it will check the data are coming or not, because everything we are controlling using the data, what data we get. So like from if I talk about like PV solar array simulator, so after solar array simulator we have a converter. So for clear picture, I will show you the that circuit diagram. Okay. So that first is like PV. You can see that gray colored is the sources, PV emulator. This is solar array simulator, fuel cell, and after supercapacitor bank, battery bank, and this DC motor and PMIG is the like wind emulator. Okay, so PV emulator. After PV emulator, we have the buck converter, and the buck converter is connected to three-phase inverter, and three-phase inverter is connected to the grid simulator, and at the PCC we have the RLC load bank. So that PV buck converter, so we are getting that data like V and voltage and current before the input of the buck converter, and output of buck converter we have the voltage. So this data we are getting in the software based on the LEM voltage and current sensor. So that layer will manage the data. So we are getting like if some data we are not getting, so it will give the alarm that like data, that particular data is not coming. Okay. So this communication and the data layer. Okay. So the four layer are there. So using that layer, we are making the system as an intelligent controller. Okay, of renewable energy sources. Now that I told you that predictive controller have the two stages, like it can forecast and the solar irradiation and the wind speed, and it can forecast the battery capacity. Like if we install battery at the starting, then it have like 100% capacity, and after 2 or 3 years, or after a few years, it will get decrease, the battery capacity will be decreased. So that controller, predictive control, also tells us how much battery capacity is remaining, and it will also predict the load, and when load are switched on and when it is switched off. So that then that predictive control is based on the AI. It will take the data, and according to data, it will predict the load switching. Okay, so that is the uh, first layer. And the second layer that we have discussed, like MPPT of solar and MPPT of wind, and how we are controlling, like or controllers we have used in the that software. In software means control software. So all control algorithms come in the real-time control layer. Okay, for controlling of fuel cell or supercapacitor or boost converter, of fuel cell, or like inverter control or battery bank, or every converter comes in the second layer. Third, that like priority based management of the sources, and the load energy management based on the priority also. Okay, which critical load and the essential unacceptable load, and communication layer. Okay, so this is the like complete circuit diagram of the renewable energy systems. Okay, which include the like all the sources of renewable, all the which include the all renewable energy sources and the energy storage also. So first we will discuss the wind emulator. After that, PV emulator, supercapacitor bank, fuel cell, RLC load, and grid simulator. Okay. So first, this is the wind emulator. So this is the it have 22 kilowatt DC motor, and that DC motor is coupled to PMIG using the gearbox, and that you can see there is a transformer also in the left side, three-phase transformer, and that single phase transformer. So DC motor we have to give armature supply to the armature and the field. So that DC small transformer, single phase small transformer is connected to the field of the DC motor, and the three-phase transformer is connected to armature of the DC motor through a rectifier. Okay, and after that rectifier we have like in the circuit diagram we have rectifier, and after rectifier we have the converter in the armature, and in field also we have the single phase auto transformer. After that we have single phase rectifier, and DC motor is connected to PMIG using the gearbox, 2:1 gearbox. After that we converted that PMIG output into AC to from AC to DC using the rectifier, and that rectified output is connected to the DC side of inverter through a buck converter. So that you can see that we call that buck converter as a generation buck after the PMIG. So that red color converter is buck converter, that generation buck, and that yellow colored is motor buck, and the blue colored is that is inverter. After that inverter we have the filter circuit and the sensors, a power analyzer, and LC filter, and after that we have the 30 kVA delta to start transformer, and the output of that transformer we connected the load bank to switch the load based on the demand, and that load is also controlled through a software. So what type of load you want to give, you can give like in kVA or okay in VA or kilowatt you can give. The whole system is connected to three-phase grid using the grid simulator. Okay, so grid you can create the grid disturbance also using that grid simulator. So like there are so much MPPT technique. So we have in this system we use the tip speed ratio to achieve the MPPT of wind turbine. So they are like hill climbing search and optimal torque control, fuzzy logic, okay, neural network based, and the model predictive control based techniques. So this type of MPPT technique we can implement in our software. So and basic we provided is the tip speed ratio. Okay, and this is the like protections devices used to control to switch on the like power supply. Okay, and fuses and the fuses and the MCB. And I said that according to user can give the wind speed manually, and the table format and the simulator format. In table format he can enter the wind speed time, but how much time, like if he enter 4 meter per second, and how much time it want to run, like for 10 second or 50 second, and what would the ramp, like if we wind speed goes from 4 to 6, then what would the ramp size, like so he can enter the ramp also. And iteration, like if he entered the wind speed like 4 meter per second, so it would run for 2 times or 3 times, so he can enter the iteration. Okay, if he enter 1, then it will run for the 1, and time what time he entered, it will run for the 15 or 20 seconds what time he entered. So in table board he can enter the wind speed data like 3 meter, 4 meter. Okay, he can enter like 4 meter, then after enter 10 meter, after he can enter the 6 meter. So according to his requirement he can enter the wind speed in table mode. So and he can see the like chart on right side when he entered the wind speed. In simulated mode, like we have like the user can have like .csv file or Excel file, so he can call that file in LabVIEW using that file path. So if we call the that table.csv file, that all data will displayed on the simulated table mode, and that data will go to wind speed as a wind speed profile. So he can see then wind speed profile here in right side of the wind profile chart. And in manual mode he can make the slider to increase like 2 to 3 years. So in manual mode he can increase the slider according to his control. Okay. And we have the like wind speed data, like what is the CP, lambda, all are the wind speed, sorry, wind turbine data. CP, lambda, all are the wind turbine data, and what would be the voltage generated. This V generation is the voltage generated at the PMHG, high generation, P generation. So here is 4 5, that is not the current. Okay, it is randomly comes. The 4543 ampere is not is the current, actual current. And the DC motor data. And at the last in the wind ammeter, that DC power, all the power at the DC link is handled by a inverter. So if any source is giving power, like wind is giving power and PV is giving power to DC link, that power is handled through a inverter. Okay, so if the inverter can uh, flow that power through it to the grid. Okay, so that inverter is controlled in hysteresis control. Normal control technique is used. Very basic control technique is used. Hysteresis control in this system. So accordingly, if we increase the voltage, so if any sources give the power through their respective converter to the DC link, so DC link voltage most probably it will increase the DC link voltage. That power will increase the DC link voltage. So inverter will maintain that DC link voltage and flow that power to the grid through it. So that's why you can see that inverter switch and the VDC reference, like what type of VDC reference, like depending on the VC. If we increase like what I have shown you, that auto transformer, so you can if you have like your own control algorithm, okay, like we are given you the hysteresis controller, but if you have developed, because all this software is customized, so you can develop your own controller and implement it. So like if you have developed your own controller and you want to test it, so you can test that controller in the lower power rating. So you can decrease that auto transformer knob to a 10 volt or 15 volt, whatever you want. Okay, it's safe limit. So according to that, the DC link voltage is 1.4 times of line to line AC voltage. If the AC side voltage line to line is 100 volt, and in the DC side you will get around 144, around 140 or 150 volt. So in that inverter switch you have to enter more than that volt. If you are getting like the VC is the DC side voltage. If you are getting like 150 volt, then you have to enter like 160 or 155. So in three phase side, in rated condition, we have the delta to star transformer. In delta side we have the line to line voltage of 230 volt. So according to that I am getting at the DC side 320 or around 322 volt, more than 322. So here I am put more than 322, so around 350. So I am maintaining the DC link at 350 using the inverter switch. Okay, and this is the wind turbine data. So there are C1 to C8, I think C1 to C8 parameters of the wind turbine. There is equation of wind turbines, CP versus lambda curve, and the CP equation, that the wind turbine equation. So depending on the wind turbine, the C1, C2, all parameter will be changed. Okay, so it have particular wind turbine data. So you can see C1, C2, C3, all are the constant. The variable is the lambda, and the lambda is the tip speed ratio, and that lambda depend on the r omega by v. V is the wind speed, and that omega is the angular speed, and r is the radius of the wind turbine. Okay, so that r is fixed, angular speed will vary, and wind speed will also vary. So at particular wind speed, like if 5 meter per second or 6 meter per second, the r and v is constant. then lambda depend on the omega, angular speed. So this is Cp versus lambda curve, or we can say it Cp versus omega curve. The omega is the angular speed of the wind turbine, okay, not the speed of the generator, because the wind turbine may have the gearbox, okay, between the turbine and the generator. So depending on that, so the depending on the gearbox ratio, that generator speed also vary. Means depending on the gear ratio, it would be like something 1500 rpm or somewhat, depending on the generator specification. Okay, and you can see that. So for obtaining, depending on that parameters, for obtaining the maximum value of Cp in that derivative, and we are getting the optimal, means at that lambda value of that 8.1, we are getting the maximum value of Cp, which is 0.479. Okay, so for particular that parameters, so maximum value is Cp is 0.479. Okay, so if you put, this is the wind turbine equation, P is equal to Cp rho A V cube by 2. Rho is the air density constant, which value is 1.225. A is the wind turbine swept area, that is pi r square. R is the radius and V is the wind speed. So power, when Cp is it particular, like Cp is derivative, and Cp is, I am getting constant value of Cp. Okay, Cp is constant, rho is constant, A is also constant, and 2 is already constant. The power generated by wind speed is depend on the wind velocity. Okay, or for particular wind turbine, it is not for all, it is particular for particular wind turbine, which we have simulated in our software. So in that, like how we are simulating the DC motor as a wind turbine. So we are getting that power. You can see the aura constant, particular wind speed, we are getting the wind turbine power. That power we equate the motor power. Okay, so that motor power is torque into omega. Okay, so like, so I of the DC motor is I into K, like to I into K is the constant for DC motor. So so we have calculated the value of constant at K5. So torque is proportional to armature current. If I K5 is constant, you can see the I armature current is proportional to torque, and in wind speed we are getting the power is torque into omega. Okay, this is constant. RPM we have, so okay, we are getting the RPM data from the motor, so we are getting torque here. So this torque and this torque we equated, and from that torque, like this is the turbine torque, and this is the DC motor torque equation. This is the turbine torque equation. First equation is the turbine torque equation, and this is the DC motor torque equation. So we equate torque, then what we will get? We will the I reference. This is the motor current reference. So this is the, we will get the motor current reference, and that reference will pass through a PI, through a feedback of the armature current, and after that we have the like pulse generation um, pulse generation mechanism, okay, in the software. So that we, and that pulse switching frequency is 10 kilohertz. Right now we are using the 10 kilohertz switching frequency to control the whole the system. Okay, and all the converters are and inverters are based on the semicron, and this is the like three-phase rectifier and the formula to get how will that VL the line to line voltage and we output a rectified DC voltage. Diagram of the boost converter, sorry, buck converter, it is written, sorry, boost converter, and the method, like what type method, the method like hill climbing method. This is the hill climbing method, and we have used that Cp because we are getting the Cp constant, we derivated, so we always we want to maintain this value. So for that we use that to achieve that, we use hill climbing to achieve the maximum power. And this is the stereo, like an NI based controller. So it have the chassis of 9064, and the module, that module This is the 906 for the chassis, and we have the we need to put the module in this chassis. So that modules are like NI 9403. This is the digital output module. So we can create the digital output, means we can create the PWM pulse also using this module. So all the converter and inverter are controlled using this module, like pulse, like PWM pulse. We are given to all converters from this module. Okay, and that module is connected through, like this is the cable. You can see this is the LAN cable. So this chassis is all based on the FPGA. So this LAN cable is connected to a PC, and that PC have PC, and the software, that library software is running in that PC. Okay, so so what we give input in the PC, we are getting the pulse from this module. And for the sensing, for the getting data from all converters and inverter, we have this module, the analog input module. This and sorry, NI9220. This is the analog input module. So we okay, this is the, like, after, you can see this is the connection before the connection, this module before the connection, and after connection this is looking like this. There's mass of wires. So this is the, like, okay, serial module connection. And this is the, like, sensor, like LEM based sensor PCB, and the card, because the stereo have the output of 5 volt, and low power also. I think it's like 40 milliampere or 20 milliampere. But yeah, that inverter needs 15 volt and around 1 ampere. So uh, for that purpose we need a power boost circuit. So this inverter pull up, we call it that power boost circuit is as a inverter pull up circuit. So it will increase the voltage also and the power also. Okay, and this is the, like, LEM voltage and current sensor. Separate PCBs are there. This is the main control panel, and the acrylic based voltmeter, sorry, panel meter. The black color is panel meter. The, like, SMPS contactors, and for production contactors and the switches are used here. So SMPS for the power supply, like inverter and the converter driver needs 15 volt power supply. For that purpose we have used the SMPS. And the LC filter, this is the iron core based inductor, and capacitor may have be placed here somewhere here. So as that are the LC filter. You can see here rating 3 millihenry rated, 75 ampere 3 millihenry. So this inductor, you can see size, you can see the size clearly, and the terminal also. So it is rated up to 75 ampere. Converters, all the converters are based on the semicron. This is semicron converters. And this is also picture of this second picture of the, like, other side view of the converter. The small single phase transformer to give the 220 volt to field of the DC motor. And it has bulky delta to star 30 kVA transformer after the inverter, 3-phase inverter. And this fuel cell back to back converter. So actually fuel cell output voltage is 45 volt at no load, and at the load it goes down up to 28 volt. So, and the ceiling voltage is 320 volt. So there is a two option to increase the voltage. One is like isolated, like dab based converter or isolated converter. So in that we have to use the isolated transformer, high frequency transformer basically we have to use. So that transformer will step up the voltage at whatever voltage it is designed. So at that time I didn't use that high frequency transformer. So we used the 3 back to back boost converter in cascaded connection. So like in 45 volt it will increase to 45 to 100 volt. Okay, up to some 2x of input voltage. and the second converter will increase 100 to 200 volt. The third converter will increase 200 to whatever we want, like 320 or whatever we want. So cascaded converter is used to boost up the voltage from 45 to 350 volt. So this is the fuel cell cascaded converter picture, and this is the picture of the three-phase inverter. The below you can see the circuit of that inverter also. Semicron based IGBT it is, and the control loop, like how we are controlling, like VDC, you can see VDC reference and the actual voltage of VDC, like DC link voltage, and what in inverter control, like 320 volt or 350 volt what we give, the actual voltage will come through PI, it will go. And ID is controlled through a DC link voltage. So power, so like ID will control the active power. And IQ, so IQ is controlled through the reactive, like I haven't mentioned here. So the Q reference we have to give, and actual Q will come. After that we have to put PI, and after PI the IQ star will come. So depending on the reactive power reference, we will get the IQ star, and that IQ star will control the reactive power. So we can operate three-phase inverter on unity power factor, and whatever we want, like on whatever want, like on reactive, and whatever power factor you want, you can operate this inverter uh, on whatever power factor you want by controlling the reactive power. Okay. So this is the designing, how we design the LC filter. So this is the formula, like DC-link voltage and ripple in the current, switching frequency, okay, modulation index. So depending on the parameters, we design the inductor and the capacitor of inverter side, okay. And the buck converter inductor, how buck converter inductor design, like ripple delta I is the ripple and the switching frequency. Boost converter formula is also there. D is the like duty, how much duty we are going to give. DC link capacitor, this is the how we design the DC link capacitor, formula of DC link capacitor. Now this is the solar array simulator. So this 5 kilowatt solar array simulator, it is basically a programmable DC source. So based on the software application, we are making to simulate as a solar array simulator. Okay, so this is a DC power supply which will work as a solar array simulator. And this is the solar array simulator. The solar array simulator is connected to the solar array simulator will mimic the behavior of the real solar panel. Okay, so lab purpose we usually use the solar array simulator to mimic the behavior of solar PV array. So we have the solar array simulator. After that we have the contactor fuse, then sensor, voltage and current sensor, and after that we have buck converter. And usually in maximum cases we use the boost converter after the solar array simulator, but the client demanded that we want a buck converter. That's why after the solar array simulator we put a buck converter. And after that buck converter we have the like three-phase inverter, and all the things are like that wind emulator, because all the sources connected to that DC link. So after DC link, for all the sources, same picture is there. Okay, and the fuses and the emergency stop switch is for on the main control panel. So if anybody's some malfunction happen, then we can push that switch, emergency stop switch, which will disconnect the all supply and the connection to DC link of all sources. Okay, so this is the like this circuit diagram solar array simulator, and how we are going to control that buck converter of. Okay, so there is a program like VMPP and IMPP. We are measuring here voltage from here. So voltage are coming, and after that this is the perturb and observe P&O algorithm, control algorithm, P&O MPPT, to control that buck converter. So these are the different control technique to control the PV converter. That if I am saying PV converter means converter after the solar array simulator. Okay, So PV, there are different control techniques. So we have implemented up to four. We have implemented four PV technique like P&O, incremental conductance, constant voltage, and the fractional open circuit voltage and fractional short circuit current. So how it works, like constant voltage, P&O and incremental conduction, like everyone I think knows about that techniques. But constant, hello. Constant voltage and constant current, how it work, like yeah, there should be a switch here, like you can see the fuse. So here is a switch, that is electronic switch, and we are putting a switch after the sensor in the parallel of plus, like between the plus and the minus, that electronic switch. So it will give the software control program will give the signal to switch to open. So when that switch will open, so we have to measure the voltage, how much voltage we are getting. Like if I am getting 100 voltage, so it is like VOC I am getting. So it is we have to run that we have to take power as much, so that voltage would be 80% of the VOC. Okay. So in that, so in like that wise, we are operating in constant voltage, and we and like constant current, we have to put a switch, electronic switch between plus and the minus after the sensor. So when we give the signal to close the switch, the ISC current will flow. So the converter will draw the power of 80% of that ISC. So in like that matter, we operate voltage in voltage, constant voltage and constant current control mode, and other are the all AI based technique which could be implemented on in our software. So this is the like software control, like PV MPPT. We can operate that PV converter in MPPT mode and in manual mode. So if you want to operate in manual mode, what power you want to give, you can give by giving the duty. Okay. And the PV and the IV curves also. So this is the MPPT tracking. This software is like that solar array simulator software, and this is the measuring software in the LabVIEW designed by MatView. So this is the MPPT solar array simulator software. We can change the parameter like how much voltage, current you can set. You can set okay, module area, and if you want to series and you want to make connection series and parallel, you can put here like how much parallel in series and parallel. You can change give input of temperature and the irradiation also. Okay, in series resistance and resistance value also. So there are many parameters you can enter according to your requirement, and that according to that parameter, that IV and PV curve will be drawn. Okay, so when we'll run this solar array simulator in MPPT mode, we will have the MPPT curve and LabVIEW also. So after that, we have the fuel cell. You can say this is the fuel cell. So we have the hydrogen cylinder. On the top of the hydrogen cylinder, we have the like meter, okay, to measure the pressure of the pressure meter. Okay, and this is the, you can see black color acrylic cased black some, you can see the black item is placed under in the acrylic box. That black is fuel cell, and the right side of that big acrylic box, there is a small acrylic box. This is a small acrylic box. So that is controller, like output power, like flow control, because we have to control the flow of hydrogen which is going into the fuel cell. For that purpose, we have that converter. That you can see that there is a meter under 2 meter. We have that SMPS type converter. So that converter control that there is the you can see the rotameter is there, and the black color is, we can sense, because we cannot, our nose cannot sense the hydrogen because it's smellless, like colorless, and the smellless, so we cannot smell. So we have to use the hydrogen sensor meter. This hydrogen sensor, I don't know what we have, what we called it, like hydrogen sensor meter or what, I don't know. So this is the rotameter, the SMPS control the flow of hydrogen using that rotameter. Okay, based and this is the like embedded controlling, like someone did it and it control according to user input. So this is the like profile of fuel cell, like when we draw the current, what would be the voltage and the power, depending on, like what I said, like when current is small, like you can see 5 ampere, voltage is 38.5 volt, and if current is 0, it is around 45 volt. So when we draw the current, voltage decrease. You can see at 40 ampere, current is 29.4 volt. Okay, so we when draw the current, the voltage of the that hydrogen output converter will decrease. So you can see this is the cascade 3 boost converter in the red color. So everywhere we have put the voltage sensor, and that cascade 3 converter connected to grid through a inverter. This is a cascade converter, boost converter, fuel cell control. So like what amount you want to give of current, like 1 to 10 ampere. So if you if you on the fuel cell and set current, so that current will match the reference current. Okay, and you will get the voltage and current data of the fuel cell. After that, we have that mounting of MCBs for the fuel cell, and this is the super capacitor bank. So we have 9 modules here. So rating of one module is 48 volt, 165 farad. So all are connected in series. So we are getting 450 volt, around 450 volt. Okay. So and that super, why we have used super capacitor, because for instant switching of the load, the super capacitor will help. Okay, and it will, because a huge super capacitor bank, so it give the power. If I draw like a 450 volt, and if I am drawing 10 ampere or 20 ampere, so it gave up to 2 minutes. Okay, so based on we have the calculation, like how much power it will give for how much time, if it what current rating. So here we have the calculation for that. So according to that, we charge, and that super capacitor is charged through a DC link. So we charge and discharge super capacitor in the battery bank through a DC link. This is the DC link. So that you can see the super capacitor is also connected to a bidirectional converter through to DC link. Okay, so this is a orange colored converter is bidirectional converter. So it charges the super capacitor bank through a DC link, and DC link voltage is maintained through an inverter. So whatever power is drawn from DC link is given by the grid through 3-phase inverter. Okay, the protection like MCB for the super capacitor bank, fuse, and the control of super capacitor bank, like same control like battery bank or fuel cell controller. So super capacitor have same control technique like fuel cell converter. Okay, so like what input we give current. So here you can see here I bet, but I bet means battery. So what type of controller is of battery? Same controller is used for the super capacitor. Same bidirectional converter used for super capacitor. And the battery is the live based program to control the super capacitor. Like for the minus you can discharge, then the minus for the charging, and the plus reference current is for the discharging of super capacitor. Okay, and you can have the graphs also. This is the battery bank, and this is the LFP chemistry based battery bank. So it has I think 9 sleeves and 1 master. So it's master slave based battery bank, because voltage is 400 volt. So it is master slave, 8 or 9 slave, and 1 is master, and 12.8 Ah. So it is 4 or 5, 4.5 kilowatt hour battery bank it is, and it has the software. So we are taking this data like battery SOC. Okay, and it has 8 slaves BMS. So we are getting 8 slave parameter also, like so 8 slaves have that every slave have the string. So we have the 8 string. So every string, data of every string we are getting in the software using the RS485. So you can see there is a like max cell. What is the cell maximum voltage, cell maximum temperature, total voltage, total current, SOC, SOH, everything we are getting in the PC. So we are getting SOC. Main what we want for the from the battery, we want SOC, main thing, voltage and voltage. The control circuit diagram of the battery same as the supercapacitor. Battery control same, battery like software version, and the RLC load. This RLC load based on the we can control this load bank in constant power and the constant current control mode. Constant power means like if you give like 10 watt, then it will operate in the 10 watt. If you give like 20 watt or 100 watt, it will operate in 100 watt. If you are giving like 200 VA or 500 VA, okay, or var, if you give an input 200 var or 500 watts, so it will operate on that power. Yeah, so in the PC, in constant power mode, in constant current mode, you have to give the current value of current like 1 ampere, 2 ampere. So that if you operate in the current mode, the power is calculated as a VA, not kilowatt or like in var. Okay, so in current control load, you have to give the input that current will match, and you will get the power rating in VA. Okay, this is the RLC load, and the RLC load is connected to the point of common coupling using the MCB, and this is the software view of RLC load. So we can enter the value and we will get the value. This is the LabVIEW GUI, and application window, like this is the complete application window. We are getting data here, all like wind emulator data and battery data, inverter data, supercapacitor, PV, all sources data we are getting in the software, and the graphs. Okay, and you can see that what I said about the PV, the solar array simulator. So in software also we are drawing the curve. So this is the PV and the IV curve. Okay, and the CP versus lambda curve. This is the for wind, and the darkened curve for the PV and the white color for the wind. Okay, all curves are there. In future, in future we can like add because when there is excess power and load is not there and battery is charged, then we can add electrolyzer, so that electrolyzer will generate the hydrogen. So when there is excess power, electrolyzer will take that power and generate the hydrogen for the fuel cell. In like that manner, we have to add the electrolyzer also in the microgrid. Okay. So thank you. Anybody have any question regarding to this system? Hello.
Hello.
Hello. Hello.
Sir, am
Yes.
I audible?
Yes. Yes. Audible. Audible. Yes, ma'am.
Sir, myself Shilpa Agrawal.
Yes, ma'am.
Sir, actually, I am working in as a faculty in electrical engineering department of Sobha Saria Engineering College, Sikar.
Yes, ma'am. Yes, ma'am.
Uh, I am having some query, sir.
Yes, sir. Yes, ma'am. Please tell me.
Sir, actually, I have seen your company's name, MatView Private Limited. It is basically in Sirohi, Rajasthan.
Yes, ma'am. Workshop in Siroi, Rajasthan, and that head office is in Delhi. So we have nearby Ahmedabad, na. So it is on the
Okay.
Rajasthan Gujarat border. So we have all the fabrication work we do from the Ahmedabad.
Sir, actually, I was like having query that we are having electrical engineering students.
Okay.
So can we have like a internship program for them?
Yeah, ma'am.
Can
Definitely.
we,
Definitely.
uh, because we are interested in signing MOU with
Hmm.
your company so that our students can gain knowledge, can
Mm-hmm.
have more practical hands-on training. Because your session was very good, sir. It was very informative.
Thank you so much.
So,
Thank you so much, ma'am.
so yes, sir. So that's why I was having this query
Mm-hmm.
that whether can I get your number so that I can contact you
Yes.
HOD.
Yes, ma'am. Thank you. Yeah, that yeah. Do you know, ma'am, Ganesh sir? That Ganesh sir will share
Yes,
you.
yes, sir. Actually, I am
Hmm.
I am for this session. I am the host also, sir. Host.
Oh, okay. It's nice to hear you, ma'am.
Yes, sir.
Mm,
So
mm,
that's why
mm.
uh, I was having that can I have your number
Yeah,
or email ID so
yeah.
that we can contact through our college?
Yes, ma'am. Yes, ma'am. I can share my email ID. I will share my email ID through like in
Hmm.
there is a like message now. I will share my email ID in the chat. So you will get my number and the email ID also.
Yes,
So,
sir. Because we were totally interested in signing
mm,
MOU with your company.
thank you,
So
ma'am.
it will be a very great opportunity for our
Mm,
students also to have a great knowledge and hands-on training with your
thank
company.
you.
And sir, whether you are also placing the students in some companies or simply you can give training to them.
Simply, we are giving training to them. After that, because the renewable energy topic is very hot topic, and we are also have the product related to electric vehicle. So, an complete electric vehicle lab, like
Yes,
for
sir.
charging, so battery testing. So we have the product for battery testing, for
Yes, sir.
chassis
Because
testing.
yes, sir. I have
Yeah.
seen the
Mm,
various
mm,
renewable energy, electrical
mm,
vehicle chargings,
mm,
and different options were there,
mm.
which are industry
English
demanding.
demanding, yes, ma'am. So,
So that's
so
why, as you are, that means Ganesh sir has approached you. So I was totally interested in your company.
Ganesh sir is my senior, so he's okay.
Yes, sir. So
Vipanchal,
please,
okay.
sir, share your please email ID so that we can
Mm,
contact through our
mm.
college.
Okay, ma'am. I
Yes,
have
sir.
said. Okay.
Oh, okay, sir. Okay.
Mhm.
Thank you, sir. Thank you.
Okay, thank you. Yeah.
Any participants want to ask some queries or any question answers? Yes, any participants? So I think, sir,
Mm.
not any
Okay, ma'am.
participants.
Okay.
Okay, thank you, sir.
Okay,
It's
thank you, ma'am.
very informative. Yes, sir. Thank you, sir. Thank you.
Thank you, ma'am. Mm.
So, participants, we will wait for around 10 minutes. And then after 10 minutes, around 7:15, we will start with our next session so that our second expert will join us soon. We will have 10 minutes break and then after we will start our next session.